Okay, so thanks a lot. Thanks a lot for inviting me here. Yeah, so I'm a Chancellor Fellow right now at the University of Edinburgh, and the main focus of my research will be multi-party computation. I've been working on this field also in the past, and in the blockchain area, of course, as I was part of the blockchain technology lab, always at the University of Edinburgh. And so this work will not be about blockchains. It will be about multi-party computation. And yeah, I hope that you will enjoy the topic. And yeah, let's go into it. I think. So as I mentioned earlier, so this is a work that will appear at Eurocrypt 2021, and it's a joint work with Vipul Goyal and Rafael Ostrowski. And so what we study here is this special notion of secure multi-party computation. Usually in secure multi-party computation, we require the parties, we have a fixed number of parties, and these parties can interact by exchanging messages with the aim of evaluating a function securely. Securely means that the adversary will not be able to learn anything aside the output of the function. In non-interactive secure computation, we want to reduce the number of interactions between the parties, but unfortunately, we know that we cannot do much better than, for example, 4 rounds if we have a broadcast channel and simultaneous message, and we are in the simultaneous message model, where basically in each round, all the parties send one message. So 4 rounds are we need 4 rounds, but we can maybe try to change the model to achieve something that requires just 1 round of interaction. In particular, we consider the case, and that's not something that we started, this setting has been considered before, the setting where we have still n parties, but there is a special party that is called the evaluator. And the setting of a protocol for non-interactive secure computation is the following. So there is a setup procedure. Someone runs this setup, and we trust this someone. And this setup then distributes some randomness, some correlated randomness to the evaluator and to the parties. So I will call R0 the randomness for the evaluator, R1 the randomness over the party P1, and so on. Now, each party here has also an input, X1 for the first party, X2 for the second, and each of these party can now use this randomness to create an encoding of the input. Okay, so the first party will run this algorithm that we call enc for encoding. Will encode it will encode the input X1, and then all these parties can send this encoding to the evaluator, which he can now perform the computation. So he can compute a function f of the inputs of all these parties that have contributed. Now, this model here requires that basically everything works fine in this model as long as only the evaluator is corrupted. So we have these additional restrictions. So not only we need this strong setup, but we also require only the evaluator to be corrupted. And as you can imagine, what we require is that in this setting, the evaluator can only learn the output of the function and nothing more than that. Okay, so how do we construct that? I mean, how people used to realize such a security notion? this security notion can be realized, and it's very similar in some sense to the notion of garbled circuits. So a garbled circuit is a primitive that where we have one algorithm that we call the garbling algorithm. So the garbling algorithm takes as input a description of the circuit that describes a function, and outputs a garbled circuit that we call capital F, and a set of labels. So a garbled circuit, one way to visualize a garbled circuit is in this way. So basically, it's a circuit that has n wires, where n is the number of inputs that the function tolerates, and to each wire we have
Sorry, Michele, there's a window overlaying your drawing, and so we cannot see everything. The window is called build order. So maybe if you move it out of the way, we will have a better image here.
What window do you see? Sorry, because I don't
yes,
see
it's
any
build
window.
Order window. The build order. It's called build old order. It's on the right-hand side.
Oh wow! Okay.
Yes, it was.
Wow, that's interesting.
Yeah.
Okay. Okay.
Thanks.
Okay. But okay. Yeah. Sorry about that. Okay. So another point is that this circuit, this garbled circuit, has n wires, and for each wire we have two labels. One that can be used to encode the input 0, and another one that can be used to encode the input 1. So the idea is that then we have an evaluation algorithm that takes as input the garbled circuit, capital F, and takes exactly one label per wire. And for example, if the first label here is the label for that represents the encoding of 0, then it's like we are requiring to evaluate the function f on the where the first input is 0. Okay, and the same holds for the second input. If we use the label L1, it means that we want the second input to be 1, and it means that we will be able to evaluate the function on this input. And yeah, this is just another example. So the point here is that if we give to an evaluator, to an adversary, to anyone, like just the garbled circuit, capital F, and exactly one label per wire, this adversary, this party, will be able to compute the output of the function with respect to the inputs encoded in these labels. And moreover, we have that the adversary cannot learn more than the output of the function. So now, as you can see, this security definition immediately gives you a way to realize a protocol for non-interactive computation, because what we can do is that in the setup phase, we know what is the function that we compute. This is fixed, so we run the garbling algorithm on this function on the small f, so that we get the labels for this garbled circuit and the garbled circuit capital F, which we give to the evaluator. And now the point here is that each party will get, for example, the first party will get the two labels for the first wire, the second party two labels for the second wire, and so on. And now, depending on what is the input of the ith party, this party can decide whether to send the label which corresponds to 0 or the label that corresponds to 1 to the evaluator. So for example, in this case, they will do exactly what they said. So, and given that now the evaluator has exactly one label per wire, he can compute the output of the function. In this example here, I was assuming that the input of each party was just 1 bit, but this can be trivially extended to the case of strings. You just need to consider a bigger and a wider garbled circuits, and so instead of giving one label to the first guy, for example, you give the first, I don't know, for example, lambda lambda labels with respect to the first lambda wires, and you're done. Okay. So, but as you can imagine, the previous model was quite restrictive, and one reason was that only the evaluator was allowed to be corrupted. And what has been considered also was a notion of called non-interactive multi-party computation, where also some of the parties, some of the other parties can be corrupted. So, for example, we can have the second party that is corrupted, and the last one, and all of those are colluding with the evaluator. So, and basically, what this security, what we want in terms of security here is that, I mean, is the best that you can achieve, and it's the best that you can hope for. And the best that you can hope for here is that the evaluator can only learn the residual function where the input of the honest parties are fixed, and but he can like change the input of the malicious parties the way he wants. So this means basically that the adversary, an adversarial evaluator that is colluding with these parties here, can in this example where the honest party is just the first one, P1, can compute f of x1, comma, any input you want to put on the remaining input slots, which means that he has a lot of freedom. And indeed, this is quite a lot of freedom. And unfortunately, the construction based on Garbled circuit does not work anymore because we were saying that the security of a Garbled circuit holds as long as the adversary has exactly one label per wire. So in this case, if the evaluator is colluding with one of those parties here, he would be able to get more than one label per wire. So the security of the Garbled circuit would be compromised, and so this doesn't really work. So, and actually, it is worth noting that this notion almost immediately implies indistinguishability obfuscation. So, as you can imagine, this means that we cannot. I mean, it's hard to hope to achieve something like that from assumptions like one-way functions. But on the other hand, if we relaxed a bit the security notion, and for example, in this work that appeared in Decrypto 2017, Beimel et al. Shows that if each party has only one bit as input, and also the number of corrupted party is just a constant in this security parameter, then we can actually achieve this notion. And the nice thing is that we can achieve this notion, and we can do it for all circuits from just relying on just one-way functions. We have also an information theoretic construction that is for circuits of depth of logarithmic depth. But yeah, so we can do that, but again, we have this restriction. Okay. Yeah, and we still don't know how to construct a protocol that tolerates a logarithmic number of corrupted parties, because this does not seem to imply indistinguishable obfuscation. So there should be hope to do it from well-founded assumptions. Okay, so okay, fine. Now it is great to have a protocol that tolerates some corruptions, but on the other hand, what is not that nice is that we have n parties, and then in order for the evaluator, even the honest evaluator, to compute the output of the function, we require all the parties to be online and to send their contribution when the time comes. And this might be unrealistic. I mean, especially because one reason why we want to rely on a notion of on such a security notion is that it's like the parties do not need to be online. At least they do not need to be online at the same time. It's like a party can wake up, can send the encoding of its input to the evaluator, and then this party can go offline again. But of course, you might have the case where a subset of these parties do not wake up, and this is completely reasonable and can happen for many different reasons. And so, yet another notion of security was considered, where you actually have a function that can be evaluated on k input. So, but you still have an n parties, and what this security notion guarantees is that as long as exactly k parties contribute to the online phase, the evaluator can compute the function. Okay, so we don't need to know what is the subset of parties that will participate in this online phase. We just know that we have n parties, and k can be any value, and this set can be made by any of those n parties. And the idea here is that no matter what the set of party is, the evaluator should only learn what is the output of the function, having received the encodings of this set of parties. In this notion, however, we have this very nice flexibility, but we are losing something, and we are losing the power or the nice feature that the evaluator can collude with the other parties. Okay. And it should be easy to see here that the construction based on Garbled circuit that I showed you before, it's not working, because what we required there was that the evaluator was able to run this evaluation algorithm, but only having exactly one label per wire. So here it's unclear how to do that. But again, there is a work in Eurocrypt 2017 of Kushilevitz et al. That shows that you can do that. You can achieve this security notion from one-web functions, actually. Okay, good. But we would like to have the best of both worlds, and so this is the first contribution of this work. So first of all, we define what it means to have the best of both worlds, which is quite intuitive, of course, and then we provide a construction. So the best of both worlds, so it's something like where the evaluator can collude with any subset of parties of sites T, where again, we want to, in this work, we consider only the case, we want to only have schemes that that rely on well-founded assumptions. So we will consider only the case where the number of corruption is constant. Okay, and moreover, we can assume that there are n parties, but in the online phase we have only k parties. Okay? So it's exactly the combination of the previous two security notions. Okay, and this is the first thing that we construct. How do we do that? So first of all, we need a special secret sharing scheme, which is based on the well-known k out of n secret sharing. So a k out of n secret sharing scheme works in this way. I assume that I hope that all of you know that, but let me do a quick recap. So let's say that Alice has a secret X, and now Alice can compute a secret sharing of X, and we call the shares with S1, S2, and Sn. Okay, so. And now Alice can distribute these shares to among this set of parties, and she can keep, for example, the fourth share for her. in this case. Okay. And now we can realize this very simple functionality, where, like, as long as k parties participate in the online phase by contributing, by just sending the share that they have received, well, then the evaluator can learn X, which is the Alice secret. Or if there are less than k shares, then the evaluator will learn nothing. Okay. So there is nothing special here. This can be seen as a special case of a threshold non-interactive NPC protocol. What we do here is defining and constructing a scheme that we call a secret sharing scheme that we call positional secret sharing. So in this notion, Alice does not have just one secret; she has k secrets. And so what we can do now is that we can run a secret sharing sharing algorithm, which takes as input all the secrets of Alice and an index 4. 4 is a position. Okay, 4 is the position that Alice, for example, has here. We can assume that all the parties have a number associated with them, and the position of Alice is 4, and so she will use the index 4 in this case. So the sharing algorithm will provide n shares. And now what happens here is that if the number of shares, as before, received by the evaluator is less than k, then the evaluator will learn nothing. None of these secrets will be leaked to the evaluator. On the other hand, if there are more than k shares and there is a share, so we take these shares, so SI1, SI2, and so on, we order them, okay? And the index of one of these shares is 4, which is the index of Alice. Let's say the sharing position 3 is 4. Okay, I'll give you an example later. I just want to give you the full definition in some sense. So what happened here is that in this case, the evaluator will only learn the jth secret of Alice. Let me give you an example. Okay, so we have here in this example just 10 parties, and Alice has 4 secrets as before, and now let's say that only the party number 2, number 4, number 7, and number 8 send a share to the evaluator. Okay, what we have here is that if you order these shares and we know who sent the share, like we see that here the share of Alice is in second position among this set of shares. So this means that the evaluator will only be able to compute the input x2, which is the input in second position here. Okay. Another example, if instead only the party 4, 5, 9, and 10 participate, then the share of Alice is in the first position, and this means that the evaluator will get only the first secret. Last example, the share of Alice can also be in the third position because 1, 3, 4, and 6 participated in the online phase, and in this case, the secret x3 could be leaked to the evaluator. Okay. If there are questions, feel free to ask. I mean, it's better if this is an interactive process. So yeah. Also because the construction, it's not difficult, but might be a bit involving. Okay, good. So if the security definition is clear, then let's see how we construct this tool. So I want to simplify to make everything as simple as possible. So let's consider the very restricted case where Alice is in the second position, and there are just only 4 parties. Okay, so the index of Alice is 2, and we have just 4 parties. So the sharing algorithm now will do the following. He does something similar for all the secret. So for x1 it does something, for x2 it does something, and for x3 it does something. But let's see what it does with respect to the secret x2, and it should be easy to extend it and to see what happens also for the other secrets. So the first thing that our sharing algorithm does is creating a 3 out of 3 secret sharing of x2 of this secret. And so we can see these shares as the left share, the center share, and the right share. What we do then is that we create a 1 out of 1 secret sharing of XL. I mean, in this case, it will be just XL itself. Okay? This is just the general way to view it. But in this specific case, S to 1 will correspond to XL. We compute a 1 out of 1, again, secret sharing of XC, and a 1 out of 2 secret sharing of XR. What is the idea here? So the idea here is that then we will assign these shares in the following way. So to the capital S. And the reason is the following. So basically, the second secret of Alice can be leaked to the evaluator only in the situation where the first party, Alice, if any of those 2 parties participate in the online phase. Okay, so what do? We give the share XL to the party P1. The share XC, we will give this share to Alice. And then the green shares here, we will give 1 share to this party, to the party with the index 3, and the other share to the party with the index 4. Now the idea is the following. The idea is that if the first party, Alice, and any of those 2 parties participate in the online phase, then we can reconstruct X2. We can reconstruct X2 because P1 will send S to 1, which corresponds to XL. Alice will contribute with XC. And since this is a 1 out of 2 secret sharing of XR, I only need 1 share to reconstruct one of those 2 shares to reconstruct XR. And once that I have XL, XC, and XR, well, I'm done because I can reconstruct X2. On the other hand, if, for example, P1 does not participate in the online phase, and let's say that, for example, only Alice and these 2 guys here, so P2, P3, and P4 participate in the online phase, then there is no way that the evaluator can reconstruct X2. The reason being that the evaluator does not have XL. And since the evaluator does not have XL, there is no way information theoretically to get some information about X2. Okay, so this very similar process with very similar intuitions is done also for the secret X1 and for the secret X3. Okay, so that's the reason why each capital S here is actually not that simple. It's made by a set of shares here, and but this is the idea at a high level. Okay. If you have questions, just please stop me or post it in the chat. Okay. Good. So, and now we are actually almost ready to construct our threshold non-interactive MPC, which I recall is a non-interactive multi-party computation protocol where only any subset of k parties can participate in the online phase, and the evaluator can collude with any of those parties that are active during the online phase. And to do that, we use, in a completely black box way, the positional secret sharing protocol that, I mean, any positional secret sharing protocol, okay, that with the definition that we gave. And we can use any non-interactive MPC protocol, okay. Just as a reminder, this is a protocol that tolerates corruptions, but it requires all the parties to be online. And as a reminder, here I will keep the description of the algorithm for each of these tools. Okay. And again, I will make a very simple example here about how our construction works. So that's why I'm considering only 3 parties. Okay, we have 3 parties in total. We have a function that has a number of input that has just two inputs. Okay, and good. So what we do is the following. So we consider the case where the input of each party is just 1 bit. Now, in this case, what we can do is that, well, we have our non-interactive MPC protocol, and we take a non-interactive MPC protocol that works in the case of 2 parties. Okay, so even if we have 3 parties, we actually consider the underlying non-interactive MPC protocol that works just for 2 parties. Why? Because this is exactly the protocol that we will use to evaluate our function f, which has cardinality 2. And what we do is the following. We pre-compute an encoding of the input 0 and an encoding of the input 1 for the first and the second slot. Okay. So just as a reminder here, if, for example, I take this evaluation algorithm here, and I run this evaluation algorithm on, for example, this first value here, C10 and C12, I am evaluating the function on the input F01. Okay. If, on the other hand, I run this evaluation algorithm on input all the red encodings, I'm evaluating the function on the input F11. Okay. So here I'm basically giving all the possible encodings that you need to then evaluate your 2 input function on any possible input. Okay. That's everything I'm doing here. Okay, what I do then is that I use my positional secret sharing. I run it with respect to the index 1. So I will do this process for all 3 parties. Okay, and I will start to run this protocol, this sharing algorithm for the first party. Okay, so and the secrets in this case are the encodings of 0. Okay, so this is the encoding. C01 is an encoding of 0 that can be used to encode the first input of the function, and this is to encode the second input of the function. Okay, so those are my secrets. I secret share them, and I give the shares. Okay, yeah, and I do the same with respect to the encodings of 1. Okay, and then I give these shares exactly as before, exactly the same way as before to these parties here. Okay. I repeat this process, exactly the same process with the same input, but with different randomness and with different index. Okay, so for example, for the third party, I will do the sharing of exactly the same secrets, but in this case, you know, I'm doing the sharing with respect to the position, to the third position and so I will get these shares that I will denote with the A. Okay, and I'll distribute these shares to the parties as before. Okay, what happens now is that let's assume that only the first and the second party, the first and the second party are aligned. So the second party, he received these shares, which are part of the setup. So those are generated from an algorithm, from an entity that we trust. But the second party will not participate in the online phase. And again, only P1 and P3 wants to participate. So how does our protocol work then? So if the input, for example, of the first party is 0, this party will send all the shares he has received, but the share that corresponds to 1 with respect to his own execution of the positional secret sharing algorithm. And the same, similarly, if, for example, the input of the third party is 1, he will send all the shares, but the share that corresponds to the positional secret sharing that was run on input, the encodings of 0, with respect to the index number 3. And the idea now is the following. So the point is that, as we said, the positional secret sharing allows reconstructing one secret as long as you have at least k shares. And in this case, we have k shares of the positional secret sharing that was run with the input 1. And basically, this means that we can actually compute the first secret that was encoded in the positional secret sharing algorithm, which is an encoding of the input 0. Now, we also note that given that P1 did not send a share, and that we need at least 2 shares to reconstruct something, well, we will not be able to reconstruct the second input, which I recall, in this case, it would represent an encoding of the input 1. Okay, so I am, just as a reminder, so the blue shares are a sharing of the encodings of 0, the red shares are shares of the encodings of 1. Okay. And I can do exactly the same with respect to the third party. Okay, so here I do not have the blue shares that are shares for the encoding of 0. So unfortunately, I can only reconstruct, I can only use the red shares, and the red shares will reconstruct an encoding of 1. Now, observe here that in the first case, I have reconstructed an encoding of 1 with the randomness R1, which basically this one is an encoding that can be used to encode an input that will go in the first slot when I'm evaluating the function, okay, in the first input slot of the function. In this case, instead, this encoding will go in the second slot of the function. So this means that I have everything I need to run the evaluation algorithm of the non-interactive MPC protocol, because I have an encoding of 0 for the first position, an encoding of 1. I mean, I have a valid encoding for the first position. I have a valid encoding for the second position, and I can compute f of, in this example here, it's f of 0, 1. Okay. So now what happens here is that, as we said, we want everything to be fine. Also in the case where, for example, the third party decides to collude with the evaluator. And now the point is that the security of the positional secret sharing here helps us, but only to some extent, because this malicious guy here can send this share to the colluding evaluator, and in this way he can compute an encoding of 0 for the second slot of the function. Okay? So this means that basically he can now compute f of 0, 1, but also f of 0, 0. But this is fine because we are using a non-interactive MPC protocol. We are using a protocol under the hood that tolerates this kind of corruption. So as long as the number of corrupted parties remain constant, we can use the scheme of Beimel et al. Of Crypto 2017, for example. So this is not an attack to our scheme. Okay. I think that I will just introduce this this other notion, and I will not go. I will not show the construction for this one. I don't think that they will have time. I mean, it's also quite dense, this presentation. So I discuss the definition. Then I'm happy to take questions or discuss anything you want, if it's fine. Okay. So the notion that I showed you before, it has nice properties, but still it's a bit unrealistic, because it's like we say, okay, parties might not be all online. Okay, fine. We require exactly k parties to be online if we want the evaluator to be able to compute the output of the function. But this is quite restrictive, because maybe, you know, I will have k plus 1 parties that are online, or k plus 10 parties that are online. And the problem is that it's unclear whether, at least by just looking at the definition, we cannot give any privacy guarantee anymore if more than k parties are participating in the online phase. And so what we consider is just that we reconsider a notion that's called secure ad hoc PSM. Basically, this notion is parameterized by two values, k and t, where the idea is that the function k is still the cardinality of the function, and t is the maximum numbers of parties that can be online, such that our protocol remains secure. So basically, what we say here is that okay, your function is still of cardinality k, but for example, you can have a k plus 10 parties that are online. Okay, k plus 100. This depends on the parameter t. Okay, but we cannot have more than t parties being online. So for example, what we consider in this work, what we construct is a protocol where you can have up to any k plus c parties online, where c is some unknown constant. So as long as c is constant, our protocol remains secure. And in addition to that, we let the input of the parties being arbitrary strings, not just bits. And now the point is that, of course, you may ask like, okay, but why are you doing it with constant? Why don't you push it further? So the problem is that also in this case, if you consider the very general definition that doesn't put any restriction on t, this notion would imply indistinguishability obfuscation. So, and again, like here, we want to provide constructions from well-founded assumptions. And a very natural question that you may ask, it's like, okay, fine, I understand that your previous definition did not allow that, but it might be that the protocol that you showed, it does allow that. So maybe it remains secure even if you have more than k parties participating in the online phase. And the problem is that that is not the case. And the reason is that if you consider this very simple example where we allow T to be k plus 1. So just one party more than k can be online. So which means that we have now this again in this very simplified in this very simplified example here. I'm assuming that only the parties with the index with indexes that go from 1 to k plus 1 are online. And this means that the evaluator now can compute f of x1 ... xk, or f of x2 ... x k plus 1. And the problem here is that if the x's have some structure, it's like the adversary can change all the input or at least the values in all the input slots of the function. Let me give you an example. So if we have 5 parties in the online phase and they all contribute with the first party contributes with 0, the second with the first contributes with 1, the second with 0, the third with 1, and so on, as you can see in the picture. Then we have that the evaluator can put in the first position 1, in the second 0, in the third 1, and the fourth 0. And then he can use completely different inputs in all the positions. And so if you think about it, this is similar, very similar to the case where the adversary is able to corrupt all the parties, and he's able to change all the input slots of this function to some extent to any value he wants. So this is just to give you an intuition that the technique that we've used before and all the techniques that try to minimize the risk that comes from parties colluding with the evaluator do not really help in this specific scenario. So we need to use completely different techniques. So I will not show you how this construction works, but I can tell you that unfortunately this construction does not rely only on one-way functions. It relies on the learning with error assumption. So this is and it's unclear how to get rid of this assumption. Of course, it would be great to have it from one-way functions. This is an open problem. And yeah, this is like this is more or less it. Yeah, so thank you very much, and happy to take questions.
Thank you very much, Michele, for the wonderful talk. So any questions from the audience?
Yeah, I suppose it was pretty dramatic. Yeah, please.
Hey, Michele, thanks for the talk. Can you reiterate again what are the practical applications of this primitive?
Okay, yeah. So I mean, this is so the point is the following: you can imagine also in the blockchain setting, for example, like you want to evaluate a function, and you want this evaluation to be done in a publicly verifiable manner. So what you can do is that you generate your setup, you distribute your you prepare your setup, and you give the the randomness, the shares to the parties that are supposed to participate. And now the point is that each of these parties can post the encoding of the input on the blockchain or on a bulletin board. And the point now is that you can see who is posting an input there, and it's non-interactive. This party does not need to interact with anybody else. And in the moment that we see, I mean, the evaluator sees on the blockchain that there are, I don't know, k or k plus 2 input, the evaluator can already compute the output of this function in a secure way. So this is quite powerful. Of course, I mean, the problem is that, again, you need this strong setup, and this is something that it's very unclear how to get rid of, unless I mean, the best that we know is how to use a PKI and then to use indistinguishability obfuscation. But then, yeah, it's not clear how practical it is. But yeah.
Great, thanks.
Okay, there was another question.
Hi, this is James. I have a quick question. I'm wondering, like, there's like outsourced NPC schemes where if where the server is computing, like where the NPC is outsourced to, if they cheat, then there are these ideas where they post bonds and those can be then claimed because it can be proved that they cheat. Do you think that is applicable here? Like if there is a malicious actor, I'm looking at your slide here.
Mm-hmm.
So, I guess my question is, yeah.
Yeah, please go ahead.
Like,
please.
No, I mean, like, do you see any application where, like, the evaluator posts a bond, but in this case, the evaluator cheats, that's okay. So, yeah, I don't know. I was just wondering whether there's, yeah.
No, I mean, yeah, I mean, the main problem is that the main problem of all these models is actually that yeah, the evaluator can cheat, and that in some way you need to assume that it's restricted to the number of corrupted parties is restricted. For example, why is it reasonable to assume that only you have only a constant number of corrupted parties? That's something that you would like to detect. You would like to be able to detect whether someone is colluding with the evaluator. But as long as they have the parties have a secure channel, the adversary is monolithic, and it's very unclear how you can detect collusion, because they can do everything offline. They can compare nodes offline. There is no, yeah.
Thank you.
Any other question? Yeah, maybe I can ask a question, Michele, and that is, how practical is the scheme? Like, do the sizes of these messages make sense in practice? Is this a pragmatic scheme?
Okay. No, so the size does not really make sense in the sense that those are polynomial. They're not insane polynomials. Like they're not something like n to at least for the first scheme, it can be practical. So it's like n square and n to the third. It can be made practical if you want. Also because previous works, for example, have been about improving the performances of these existing schemes with all the limitations they had, but there was a lot of work in improving the performances. So it is possible. The scheme that you have in the paper, it's not at the moment, but it's possible. The last scheme, the one that allows more than k parties to be online, the parameters are a bit crazy because yeah. But let me say that we did not focus on performance here. So this was more like a feasibility result and show what you can do from reasonable assumptions in some sense. But I think that there is room to make this reasonable. Yeah.
Okay, that makes sense. Okay, any other question for Michele? We have a couple minutes. Okay, if there's no further questions, let's thank Michele for the talk. And thank you everyone for attending once again. And we invite you to come back next week for our usual meeting. Next week, we will have Sandra Corretti trade. So have a nice day, everyone, and have a nice rest of the week as well.
Thank you very much. Bye, everyone.
Thank you. Bye-bye.
Bye.